Hi, today we are going to see problems related with magnetic effects of current, part 2. Whenever a current is passing through a coil or a conductor or a wire, there exists a magnetic field. This is the basic principle of this topic. The magnetic field of induction is given by Biot-Savart law. Wire current is passing through. You are considering a small element CD of the wire. Then what is the magnetic field at the point P is given by Biot-Savart law. dB is equal to mu naught by 4 pi IDL sin theta by R square. So this is Biot-Savart law basic expression. We have two applications in Biot-Savart law. One is current carrying due to infinitely long charged wire. What is a magnetic field at a point outside? By Biot-Savart law, I am going to express B is equal to mu naught I by 2 pi D or 2 pi A. Anything. This is the distance from the center to the point P. And second application is magnetic field of induction along the axis of a circular coil carrying current. Center, radius A, distance X. So B is equal to mu naught Ni A square by 2 into A square plus X square whole power 3 by 2. This is magnetic induction at a point due to N-turn circular coil. Okay. Then torque experienced by a magnetic dipole. Coulomb's inverse square law, similar to electrostatics. Coulomb's inverse square law in magnetism. Force between two pole strength is equal to F, that is mu naught by 4 pi Qm1 Qm2 by R square. Qm1 is the magnetic pole strength of one side, Qm2 magnetic pole strength of the other side. Are two different poles. It might be a like pole or unlike pole. Like poles means repel, unlike poles means attract. One is Qm1, another is Qm2. Then F is equal to Qm into B. This is the relation connecting magnetic field and force. You want to calculate force, Qm into B. B is called magnetic induction. Or B you want to calculate F by Qm. Okay. Force per unit charge is called electric field. Force per unit pole strength is called as magnetic field. Okay. Next. What is a torque experienced by a dipole when it is placed in a magnetic field? Torque tau is equal to mb sin theta. Where capital M we call it as magnetic dipole moment. Capital M is equal to Qm into 2L. Qm we call it as pole strength of the magnet and 2L we call it as length of the magnet. This is measured in ampere meter. This is measured in meter. So unit of pole strength is ampere meter square. Okay, fine. Next, basic formulas alone. We are not going to discuss in detail. Basic formulas alone we are going to see. When you place a charge in a uniform magnetic field, there exists a force. F is equal to BQV sin theta. Whereas when you keep a charged conductor in a magnetic field, then F is equal to capital F is equal to BIL sin theta. Force experienced by a single charge Q is equal to E, where N is called the total number of charges present in that particular wire. So the total value is BIL sin theta. Vector form you want to write means F is equal to IL vector cross B vector. Okay. Based on this concept only, this is force due to single wire. Suppose we have two wires. Two wires we have separated by a distance A. Magnetic field due to first wire B1. Magnetic field due to second wire here. First wire magnetic field is here. For second wire current I1, current I2, magnetic field is here. These two experience a force. So when current flows in the same direction of both the wires, then the force of attraction will take place mu naught by 4 pi I1 I2 by R. Given medium means this should be mu. Okay. Based on this only, we are going to define what is called ampere. What is called ampere? Ampere definition. Mu naught by 2 pi, that is mu naught by 2 pi I1 I2 by R. That's okay. No problem. Then moving coil galvanometer. Torque experienced by a rectangular coil carrying current placed in a magnetic field. Torque tau experienced by a magnet when it is placed in a magnetic field. NBIA sin theta. This is torque. Moving coil galvanometer. Moment of deflecting couple is equal to moment of restoring couple. Deflecting couple is NBIA. Restoring couple is G theta, where I is equal to G by NBA into theta. G by NBA permanently constant. So this values will not change. If I changes, theta also changes. That is deflection produced. Okay, fine. Then conversion of galvanometer into ammeter, conversion of galvanometer into voltmeter. Galvanometer into ammeter. Galvanometer into voltmeter. You have to connect a low resistance in parallel with the galvanometer. Why means if you don't connect low resistance in parallel, most of the current will enter. The wire will break. So we have to connect a low resistance. So when current comes through that, since you are connecting a low resistance with the galvanometer, most of the current will go to the shunt. That is called shunt connection. Connecting in low, in parallel. Parallel connection is known as shunt connection. S is equal to Ig by I minus Ig into G. S is called the low resistance which has to be connected. Ig galvanometer current, I is called the total current, G is called the galvanometer resistance. Okay, fine. Convert of galvanometer into voltmeter. You have to connect high resistance in series. This is connecting low resistance in parallel. There you have to connect high resistance in series. Ohm's law, V is equal to I into R plus G. R plus G is equal to V minus G by I. No, V by I. So R is equal to V by I minus G. R is equal to V minus I into G by. Okay, basic formula. This itself will do. This is not at all necessary. Just for simplification, I have done. So these are the basic formulas related with magnetic effect of current. Keep these things in mind. We'll go to the problems. Right. Now we are going to continue the problems. We have just seen the formulas related with magnetic effect of current. Now we are going to see the problems related. First problem, a circular coil of wire consisting of 100 turns, each of radius 8 centimeter, carries a current of 0.4 ampere. What is the magnitude of the magnetic field B at the center of the coil? Biot-Savart law application we have seen. In that second application, circular coil carrying current along the axis. But the question is, what is a magnetic field at the center of the coil? B is equal to mu naught Ni by 2R. This is the formula for magnetic field due to a circular coil carrying current at the center. Okay. The values, number of turns 100, current 0.4 ampere, radius 8 centimeter. Mu naught 4 pi into 10 power minus 7. Number of turns 100. This is 0.4 divided by 2 into 8 centimeter. 8 into 10 power minus 2. So you will get B will be 3.1 into 10 power minus 4 Tesla. State substitution, magnetic field at the center of the circular coil carrying current. Second problem. A long straight wire carries a current of 35 ampere. What is the magnitude of magnetic field B at a point 20 centimeter from the wire? Infinitely long straight conductor carrying current. Again, Biot-Savart law application. B is equal to mu naught I by 2 pi R. 4 pi into 10 power minus 7. Current value 35 ampere at a point 20 centimeter. 35 ampere at a point 20 into 10 power minus 2. So the magnetic field value for a straight conductor is 3.5 into 10 power minus 5 Tesla. This is Biot-Savart law circular coil carrying current. This is Biot-Savart law application. Infinitely long straight conductor carrying current. Okay. Now third one. A long straight wire in the horizontal plane carries a current of 50 ampere in the north to south direction. Give the magnitude and direction of B at a point 2.5 meter east of the wire. 2.5 east of the wire. First, we'll calculate the magnetic field. What is the magnetic field? Based on this formula, we'll calculate. Then right hand thumb rule. Simple. B will be mu naught I by 2 pi r 4 pi into 10 power minus 7 into the current passing through is 50 ampere by 2 pi into radius is 2.5 meters. This is 2 times 25 into 10 power minus 1. 2 times. So 4 into 10 power minus 1 numerator plus 1. 4 into 10 power minus 6 Tesla. East of the wire means magnetic field is towards east, means in the perpendicular plane only the direction. Question is, give the magnitude and direction of B. What you have calculated is magnitude. The direction will be according to right hand thumb rule. It will be in the perpendicular plane. Okay, fine. Next, fourth problem. A horizontal overhead power line carries a current of 90 ampere in east to west direction. What is the magnitude and direction of magnetic field due to the current 1.5 meter below the line? (1.5 meters below the line). First, we calculate based upon the formula straight wire mu naught I by 2 pi r. So let us calculate the magnitude. Current given here is 90 ampere, 1.5 meter below. 4 pi into 10 power minus 7, 90, 2 pi into 1.5 meter below. 15 into 10 power minus 1. 15 and 90 is 6 times. 10 power minus 6 Tesla. Below the line, below east-west direction. Below the line is a question. See the question. What is the magnitude and direction of the magnetic field due to the current? Below the line, current passing horizontal overhead power line in east-west direction. So downwards current, downwards direction of magnetic field. Downwards means east-west, downwards means it should be south, along south. Magnitude and direction. Perpendicular plane, whatever direction your current is passing through, perpendicular plane only magnetic field by Oersted experiment. Basic concept. 5. What is the magnitude of magnetic force per unit length of the wire carrying a current of 8 ampere and making an angle of 30 degree with the direction of uniform magnetic field of 0.15 Tesla? Question is, force per unit length you have to calculate. Whenever a current carrying conductor is placed in a magnetic field, there exists a force. The total force is BIL sin theta. Question is, force per unit length, F by L, Bi sin theta. Magnetic induction given 0.15 Tesla, current is 8 ampere, theta is 30 degree. 0.15, this is 8 ampere sin 30. 12 sin 30 is half. So 6 Newton per meter. Question is 8 into 0.15. 8 into 15 is 120. So it is 1.2. So 0.6. Points per unit length. Force per unit length. So Newton per meter should be the unit. Okay. Fine. Next. A 3 centimeter wire carrying a current of 10 ampere is placed inside a solenoid perpendicular to the axis. The magnetic field inside the solenoid is given to be 0.27 Tesla. What is the magnetic force on the wire? Same formula. F is equal to BIL sin theta. Instead of giving B directly, this is magnetic field due to the solenoid they have given. Generally, magnetic field value they will give and we will substitute. Here, for a solenoid, it is given. So, what is the force experience? Force experience, basic formula, PIL sin theta only. So, there is no change in that. So, in the case of a solenoid, what is the concept? That we have to calculate. F is equal to BIL sin theta. What is the value, ma? B value 0.27 Tesla, current 10 ampere, length 3 centimeter wire, 3 into 10 power minus 2, placed perpendicular, then theta should be 90. So F is equal to, this is 27 into 10 power minus 3, 10 power minus 5. This is 110, 10 power minus 4. 27 into 3, 81. Sin 90 is 1. So 88.1 10 power minus 3 or 81 into 10 power minus 4 Newton. This is the force experienced by the conductor. State substitution. Ma? Question number 7. Two long and parallel straight wires A and B carrying current 8 ampere and 5 ampere in the same direction are separated by a distance of 4 centimeter. Estimate the force on a 10 centimeter section of the wire. Two wires, when current is passing through in the same direction, by Fleming's left hand rule, there exists the force of attraction. Force due to single wire when a magnetic field, current carrying conductor placed in a magnetic field, we have seen F is equal to BIL sin theta. Whereas two parallel wires carrying current, then force per unit length, capital F is equal to mu naught I1 I2 by 2 pi r. This is force per unit length. Okay. Value, current 8 ampere and 5 ampere, distance 4 centimeter. F is equal to 4 pi into 10 power minus 7, 8 ampere into 5 ampere divided by 2 pi. Distance 4 centimeter. 4 into 10 power minus 2. Correct? So 2 times. This is 2 times 4 into 5, 20. 10 power minus 7 plus 2, 10 power minus 5. 2 into 10 power minus 4 Newton per meter. But the question is, what is the force experienced for 10 centimeter section of the wire? F is equal to small f into L. Force per unit length. So force means you have to multiply by the length, that's all. So it should be, or you can put like this, F is equal to capital F into L. Capital F is force per unit length. Length cancel means you will get force. Unit wise. Any particular thing, unit wise you have to cross check. Okay, fine. 2 into 10 power minus 4, 10 centimeter. 10 into 10 power minus 2. So 2 into 10 power minus 6, 10 power minus 5 meter. Correct, Amma? Straight substitution. Small change, that's all. Force per unit length normally we will calculate. Here force for a given length they are asking. Eighth problem. A closely wound solenoid 80 centimeter long has 5 layers of windings of 400 turns each. Diameter of the solenoid is 1.8 centimeter. If the current carries is 8 ampere, estimate the magnitude of B, that is magnetic field, inside the solenoid near its center. Magnetic field due to a long solenoid carrying current. Formula B is equal to mu naught Ni, where N is called number of turns per unit length. If they give number of turns, total number of turns, put that one divided by length of the solenoid, we have to substitute. Okay. Now we'll go to the problem. Question is 5 layers, each of winding for 400 turns. So number of turn is 400. Like that, 5 layers are wounded. So naturally, in this case, we have to multiply by 5. Generally, number of turns alone will be given. In this, to confuse you, an extra term is given. 5 layers. Each layer 400 turns. Second layer 400 turns. Third layer like that. So we have to multiply by 5. By length of the solenoid. What is length? 80 centimeter. So 0.8 meter. 80 into 10 power minus 2. So small n is equal to 5 times. So 25 into 10 power 2. 2500 turns per unit length of the wire. Therefore, B will be mu naught 4 pi into 10 power minus 7 Ni 2500 into current. Current is 8 ampere. 4 into 2500. 100 means 3 zeros. There 2 zeros, here 2 zeros. So 8 into 10 power minus 7 plus 4. 8 into 10 power minus 3 Tesla. 8 into 10 power minus 3 Tesla. Correct? So this is 8th problem. 9th problem. A square coil of radius 10 centimeter, 20 turns, carries a current of 12 ampere. Angle subtended 30 degree with the direction of magnetic field 0.8 Tesla. What is the magnitude of the torque? This is the question. So, rectangular coil. This is the rectangular coil carrying current placed between the magnetic field of north and south. So, whenever a current carrying conductor placed in a magnetic field directs the force, here 4 conductors. We are assuming this to be a 4 conductors. These two forces, magnitude is same, direction opposite, cancel. These two magnitude is same, but line of action is different. So it will try to rotate the coil. That rotating force only we call it as torque. That torque only we have to calculate. So torque tau is equal to NBIA sin theta. Value of number of turns 20 turns. B value 0.8. Current passing through 12 ampere. And the radius square coil of side 10 centimeter. Area is side into side 10 centimeter. So 10 into 10 into 10 power minus 2 minus 2 minus 4. Angle subtended 30 degree. So sin 30. Square coil. What? Basic formula is same. NBIA sin theta for rectangular coil or square coil. Basic formula is same. Top and bottom opposite forces, same magnitude and opposite in direction nullify. Sideways it will try to rotate the coil. Concept is same whether it is a rectangular coil or a square coil. Okay. Simplify this. You will get an answer 0.96 Newton meter. Newton meter is a unit of torque. Okay. 10th one. In a chamber, uniform magnetic field of 6.5 Gauss. One Gauss means actually 10 power minus 4 Tesla. So confuse you only are giving in terms of Gauss. SI unit is Tesla only. 1 Gauss means 10 power minus 4 Tesla. An electron is shot into the field with a speed of 4.8 into 10 power 6 meter per second, normal to the field. Explain why the path of the electron is a circle. Determine the radius of the circular orbit. Whenever a charged particle enter in a magnetic field, it experiences a force. Current carrying conductor BIL sin theta. Single charge means BQV sin theta. No, sir, only one electron, BeV sin theta. When it entered, every time its path changes. Path changes. Magnitude remains constant, direction is changing. Means only concept, only possibility, it should move in a circular path. Same magnitude, direction alone changes. Path of the electron changes when it is moving in a magnetic field. So that possibility should be, it should move in a circular path. Second part, we have to calculate the radius. Formula F is equal to BEV sin theta. Circular path F is equal to mv square by r. In our case, everywhere tangent and normal direction. Circular path means towards the center there exists a force. So that theta should be 90. So BEV sin 90 is equal to mv square by r. One v get cancels. R is equal to mv by BE. R, mass of the electron 9.1 10 power minus 31. Velocity 4.8 into 10 power 6. Divided by magnetic induction value 6.5 Gauss. 6.5 into 10 power minus 4, because 1 Gauss is 10 power minus 4 Tesla, into charge of an electron 1.6 10 power minus 90. 9.1 into 4.8 divided by 6.5 into 1.6. 10 power minus 31 plus 6 is minus 25. This is minus 23. Numerator plus 23. Minus 25 plus 23. It should be 10 power minus 2. Rearrange and simplify. You are getting an answer 4.2 into 10 power minus 2. That is 4.2 centimeter. Correct? This is 10th problem. 11th one. In the previous problem, obtain the frequency of revolution of the electron in its circular orbit. Does the answer depend on speed of the electron? Explain. Frequency basic formula is 1 by time period. Cyclotron only we will do this. Centripetal force with magnetic field force. When you equate, the revolution of electron has got certain period of revolution. Frequency should be 1 by time period. Formula BQ by 2 pi m. Time period is 2 pi m by BQ. Frequency is BQ by 2 pi m. In our case, an electron. Question. So it should be BE by 2 pi m. Magnetic field. Previous problem only question. Previous problem, magnetic field is 6.5 into 10 power minus 4. Charge 1.6 10 power minus 19 by 2 pi. Mass of the electron 9.1 into 10 power minus 31. This formula is independent of speed. BE by 2 pi m, it has got no connection with the speed. Okay. So directly we have to substitute the formula and calculate the frequency. No, it does not depend upon the speed of the electron. The answer is 18 into 10 power 6 hertz. 18 megahertz. 18 megahertz. Okay. 12th problem. The wire which connects the battery of an automobile to its starting motor carries a current of 300 ampere for a very short time. What is the force per unit length between the wires if they are 70 centimeter long and 1.5 centimeter apart? Previously, we have calculated parallel wires. F is equal to mu naught I1 I2 by 2 pi r. 4 pi into 10 power minus 7. Current I1 and I2. 300 ampere. Both 300 ampere. 300 into 300 by 2 pi. Separated by a distance of 1.5 centimeter. Excuse me. So this is 2 times. 2.5 and 3 is 2 times. So 4, 10 power minus 7, minus 5, minus 3. This become plus 2. 10 power minus 1. 0.4 Newton. 0.4 Newton. No. 2. One more 3 is there. This is 2 times. This is 2 times. 2 into 2, 4. 4 into 3, 12. So 1.2. 1.2 Newton is the Newton per meter. Question is, what is the force per unit length between the wires if they are 70 centimeter long? Therefore, F is equal to capital F into L. Capital F is 1.2. This is 70 into 10 power minus 1 0 is between 12 sevens are 84. 84 into 10 power minus 2 Newton. 0.84 Newton. Correct? Like this, we have done one problem in the previous topic. Similar. First, you calculate the force per unit length. Then you calculate the force. That means you have to multiply by the length with the answer. Okay. Question number 13. A circular coil of 20 turns, radius 10 centimeter, is placed in a uniform magnetic field of 0.1 Tesla, normal to the plane of the coil. If the current is 5 ampere, what is the total torque, total force on the coil? Third one, average force in each direction. Average force on each electron in the coil due to the magnetic field. 0.1 Tesla, number of turns 20. Then torque, force, average force you have to calculate. Given Cross-sectional area 10 power minus 5. Electron density 10 power 29. First part, torque tau is equal to NBIA sin theta. Number of turns is placed in a uniform magnetic field, point 1 Tesla, normal to the plane of the coil. Normal to the plane of the coil it is placed, but magnetic field is parallel. Plane of the coil and the magnetic field. So direction of current and direction of magnetic field both are same. So you need not substitute here. Straight theta 0, therefore torque is 0. Angle between current element and normal only we have theta. Okay. Second part. What is the force on each electron? F is equal to BeV sin theta. In our case, BeV. This is different. Rectangular coil formula is different. This is different. So, B into I is equal to NEAVV. So, V is equal to I by NEA. BE into I by NEA. Cancel. So, F is equal to B into I by N into A. This is the force. B into I by N into A. So force on each electron, we have to calculate that value 0.1 Tesla. F is 0.1, B value 5 ampere by what is the value given? Number of electrons, electron density 10 power 29. Area 10 power minus 5. Simplify, you are getting the force as 5 into 10 power minus 25. 5 into 10 power minus 25 Newton. And one more is asked. What is the total force on the coil? This is average force of an electron you have calculated. Total force is asked. In the case of rectangular coil, total force is upward and downward. These two forces have same magnitude. Same magnitude you are getting. Direction is opposite. So it will get cancelled. Net force is 0. Net force is 0. Correct? Excellent problem. Torque, total force or net force, these two are 0. Then force due to any one side, BIL sin theta. Single charge, so BQB sin theta. This is the formula. 14th problem. A galvanometer coil has a resistance of 12 ohm and the meter shows full scale deflection for a current of 3 milliampere. How will you convert this into voltmeter of range 0 to 18 volts. Conversion of galvanometer to voltmeter. In that case, we have to connect high resistance in series. High resistance in series. So that value R is equal to V by Ig minus G. This is called a galvanometer resistance. You can put capital G also, or you can put RG also. Both are same. Galvanometer resistance. Value 18 volts, 0 to 18 volts. Current is 3 milliampere. 18 by 3 into 10 power minus 3. Galvanometer resistance given as 12 ohms. So R will be 6 into 30, 10 power minus 3, numerator 10 power 3 minus 12. 6000 minus 12, 5988 ohms. So this much ohm resistance should be connected in series with the galvanometer. That you have to write. Okay, ba? Fine. 15th problem. A galvanometer has a resistance of 15 ohms and meter shows full scale deflection for a current of 4 milliampere. How will you convert this one into ammeter of range 0 to 6 ampere? Conversion of galvanometer to ammeter. We have to connect a low resistance in parallel with the galvanometer. That is, S is equal to Ig by I minus Ig into G or into Rg. Anything you can write. S is called shunt resistance. Low resistance connected in parallel with the galvanometer is called shunt resistance. Shunt means connecting in parallel. Okay, now the data. Galvanometer current 4 milliampere, total current 6 ampere. 4 into 10 power minus 3, 6 minus 4 into 10 power minus 3 into resistance of the galvanometer, 15 ohms. So value of S should be 0.01 ohms. Connected in parallel with the galvanometer. That point you have to write. Okay. 16th problem. An alpha particle crosses a space without any deflection. If electric field is 8 into 10 power 6 volt per meter, magnetic field is 1.6 Tesla. Calculate the velocity of the particle. Undeflected. The basic concept, when it is moving undeflected, electric field force and magnetic field force both are equal. So BeV sin 90 is equal to E into E. Magnetic field force, electric field force. E get cancelled. V is equal to E by B. So value E will be 8 into 10 power 6 divided by B value 1.6 Tesla. So this is 5 times 5 into 10 power 6 meter per second. 5 into 10 power 6 meter per second. Straight up. Undeflected means both forces are equal. That is the concept. Seventeenth problem. A circular loop of area 0.01 meter square carrying a current of 10 ampere is held perpendicular to a magnetic field of intensity 0.1 Tesla. Calculate the torque on the loop. Already we have seen the formula for torque. Tau is equal to NVIA sin theta. Number of turns given 1. Current is 10 ampere. B will be 0.1 Tesla. 1.1 Tesla. Current is 10 ampere. Area value 0.01 meter square. Sin 90. Because in the question is held perpendicular to the magnetic field. That is a concept. Perpendicular to the magnetic field. So tau will be sin 90 is 1. This is 10 power minus 1. This is 10 power minus 2. So 10 power minus 3 into 10. 10 into 10 power minus 3. 10 power minus 2 Newton meter. 0.01 Newton meter is the torque. Okay. 18th problem. A galvanometer has a resistance of 10 ohm and the meter shows full scale deflection for a current of 1 ampere. Shunt resistance required to convert the galvanometer into ammeter range 0 to 100 milliampere. You have to calculate the shunt resistance. Already we know the formula for conversion of galvanometer to ammeter. S is equal to Ig by I minus Ig into G you can put, or into Rg you can put. We have to connect a low resistance in parallel. So S will be, what is the current given? 10 power minus 3. That is 1 milliampere. This is 10 ohms. Total current 100 milliampere. 100 minus 1 milliampere you can take it out. Cancel 10 by 99. Nearly 0.1 ohm. So nearly 0.1 ohm should be connected in parallel with the galvanometer. This is conversion of galvanometer to ammeter. Okay. So we have seen the basic formulas of magnetic effect of current. Based on this, we have done some problems. Now, using Coulomb's inverse square law, what is the magnetic field along the axis of a circular coil carrying current, axis of a conductor carrying current? Along the bar magnet, along the equatorial line, what is the magnetic field? What is called current loop in a magnetic field? What is called Bohr magneton? This and all we will discuss in the next part of magnetic effects of current. Okay. Thank you. We'll continue.